Hi, everyone. Welcome to the Machine Learning at Georgia Tech seminar. And it is my great pleasure to introduce Adriana Kovashka. Adriana is an assistant professor in computer science at the University of Pittsburgh. Her research interests are in computer vision and machine learning. She has authored numerous papers at top AI conferences. She has served as an area chair for many of them. She's going to be serving as a program chair at ICCV 2025. Her research has been supported by the National Science Foundation, Google, Adobe, Amazon. What I personally really enjoy about Adriana's work is that it tends to be a breath of fresh air. I think she goes after a lot of problems and questions that aren't necessarily mainstream, but I think are fascinating. And I think you'll see some of that in her talk today. And so with that, thanks, Adriana, for being with us, and I'll let you take it from here.
Thanks, Debbie, for the invitation and the introduction. So the title is Reasoning About Complex Media from Weak Multi-modal Supervision, which there's kind of a lot of words here, but hopefully this slide can actually explain what I'm trying to do. So what I'm interested in is understanding the rhetoric of multimodal media. And, I probably don't need to convince you, especially this week and this month, that this is important. But, understanding how media affects opinion is fairly tricky. So we want to understand the agenda or intent of the media. So we've looked at more recently political articles, a little bit further back, but what I'll talk about first, visual advertisements. And the challenge here is, so these are very creative. They target human audiences, but also data is limited in the sense that images that have intent, like images in political articles that do have intent, or advertisements, which a designer actually had to spend some time to create, they're not as plentiful as general images. And also the supervision that we have on them is limited in terms of count and also in terms of extent, because advertisements are very appeal to human knowledge in even more so than other images, and so annotating all the knowledge that you need is maybe not so feasible. One nice thing about these media that I look at is that they have both visual and textual aspect. But generally, so the text, you can say, provides some sort of supervision to understand the images, but the relation between text and image is indirect, unlike sort of other problems we've looked at in vision and language. So even though text is a type of supervision for the images and what they show, it's a kind of noisy supervision. So what I've been interested in more recently is, still within these applications, how we can learn useful models for some of these tasks from noisy data. Just as a motivational slide that I've used for a while, it comes from kind of my background in media studies. The images at the top are two images that won awards that have been very influential. One is from the 60s, one is from the 90s. So these had real, social impact. At the bottom are a bunch of advertisements. The first one probably everyone has seen. The second group of the absolute ads, I don't so much care about their impact in terms of increasing market share of vodka by whatever factor, but I'm interested in them being extremely creative and extremely challenging. So probably, with a second of thought, we can all figure out why this is absolute Chicago because of the wind, and this is absolute peel because this is a, orange peel or whatever. But, these are going to be extremely challenging for vision algorithms to infer. Why is this Chicago? Why is this a peel? So we, to get started, we formulate this task of decoding image advertisements as understanding the message that this ad is trying to convey. And, state-of-the-art vision systems are not good at this just because they're not trying to be good at this. So we can recognize concepts in these images, and this is from actually a few years back, so it's probably even better now. We can caption these images with, fairly accurately, but the problem is that in terms of what this image means, which is really, the reason for creating this image, in terms of what it means, without, before our work, vision algorithms weren't able to do this, and it was only because they weren't looking at this aspect of persuasive images. So one explanation of what this means is which is from an annotator, is food at Burger King must taste really good, since even the competitor's employee secretly buys it. And so we know it's secret because of the trench coat. We know that this is Ronald McDonald. There's a lot of contextual knowledge that you need to understand this. And I think that's why, it's an interesting problem. So explicitly, some of the challenges that, some of which we've looked at, some of which we haven't looked at purely visually, these ads have, I think about a small fraction of ads, but non-trivial fraction of ads have these atypical objects that they feature that are obviously not photorealistic, and so vision algorithms will have a lot of trouble understanding them. You have this deer made of junk, you have this cow made out of fruit, you have these lungs that are actually trees, you have this owl made of coffee beans. So developing representations that are robust to these is something that I'm interested in. So we actually have a recent grant on this topic, but it's not something that I'll talk about in this talk. Another thing that I think is really cool is how ads, even though these are static images, imply a certain physical process. And this process actually relates to the point that the ad is making. So these two are a little bit less obvious maybe, but this one, we can all agree the earth is melting. This, if you think about what's going to happen next, this bear is going to be crushed by the arms of the clock. And so it's saying something about, I think this says that every 60 seconds a species dies out. So basically animals' time is running out, so we need to rescue them now. There's, in terms of, common sense, if you will, there's these symbolic associations that ads rely on, like guns are dangerous here, people are fragile, and oven mitts are used for hot stuff, and it's actually a pun because it's hot like here, this ketchup is hot like spicy, not hot like temperature. So there are these symbolic associations, and we've looked at that a little bit, how to leverage that to understand the messages of ads. There's also an interesting vision language aspect, which is that the type of text that ads feature is what I'm going to call a slogan, is often is more of a metaphorical use of the text sometimes. So here, this is indeed a winter collection. So this is kind of a literal use of the word, of the phrase winter collection. Here, it's not. So she's dressed in cardboard boxes, and I believe the intent is to, for this ad to evoke ads like this in your mind, but kind of make the state of this person even more, seem even more tragic, as a call to action to, in this case, help prevent or work against human trafficking. So this is a public service announcement against human trafficking. This is a typical clothing ad. So the relationship between image and text in these two ads, especially in this one, is very, very abstract and very tricky, but also very interesting. So to start, we collected this advertisement data set. This is the image data set of 64,000 ads with a variety of annotations, like the topic of the ad. So basically, if it's a product ad, what is it trying to sell? If it's a PSA, what is it a PSA about? We have a bunch of sentiment annotations, like what sentiment is this ad trying to evoke? Is it trying to make you hungry? Is it trying to make you scared? Is it trying to cheer you up? This is kind of the main thing we use, which are these action reason statements, like a natural language answer to what does this ad suggest you should do, and what reason does it provide for taking the suggested action, and a few other types of annotations. We also have a similar data set with fewer videos, which we've annotated with some of the same types of annotations. So in terms of decoding advertisements, again, this is a kind of one of the core tasks that we've tried to explore. What message does the ad convey? We call the action, and what arguments does it provide for taking the suggested action is a reason. And so this you can think of at a high level as a VQA task where the answer is open-ended. There's different ways we've actually gone through for how we actually formulate this task in practice. One thing that we kind of settled on, because it's so challenging, is a multiple choice task. We're given k options for the action reason statements. The algorithm needs to pick the one that matches the image. And just to give you a sense of how challenging this is, even if people actually did understand the ad, which is not always the case. Here I have this ad, and we have 3 annotations that are all correct. So these are all actually matching this image. And this says Evian live young, and the annotations are I should drink Evian. So this is our action, and because it helps you recover, because it keeps us young, is the reason that the ad provides. So here's an example method among the recent ones that we came up with for this task, which builds on prior methods. So here we have this, now it's a PSA that says read the road, and it shows you a crashed motorcycle, and it's about basically being careful. The slogan says read the road and you won't need as many new parts. So we want to do this. We have a metric learning task where this image needs to be matched with statements like this. I should be careful on the road so I don't crash and die. So this is our action reason statement. And it should be it shouldn't be matched, so it shouldn't be close. The visual representation shouldn't be close to something like this, which says I should buy this motorbike because it is fast. So we have embeddings for the image and the pieces of text. What goes into our image embedding is most standard, just some image regions with learn attention scores. We have a representation of the slogan, which is embedded in the ad, so that's this. To leverage our idea of basically ads relying on symbols, and this comes from media studies theory as well, we have a symbol classifier. So our symbols are things like danger and nature and technology, all kinds of concepts that are abstract but can be demonstrated with specific objects. And I have a slide to go into that a little bit more next. But we basically have a symbol classifier that outputs how likely it is that this image contains any of these specific symbols. And then just because we don't actually have anything like object annotations on these images, we run a dense captioning algorithm to get predicted descriptions of objects in this image, and all that goes into our image embedding. So the symbolism, we basically so I want to go further on this and go beyond what we've actually done. But what we have done is that we have collected annotations for people about a bunch of symbols or concepts and types of images that refer to this concept. So types of images that are signifiers, as you might call it in the media studies literature. So signifiers for something that's called a signified, or in other words, the concept. So here we have different images that show danger, that symbolically refer to danger, images that refer to being natural or being healthy, which are kind of related. These are symbols for strength, often muscles or strong cars or whatever. Things that refer to speed, like bullets and rockets, and things that refer to energy. But going back to the actual method, in a high-level overview of results, basically this here we're trying to retrieve an action reason statement, so what you should do and why, and we show accuracy and rank, and we separately show result where accuracy obviously should be high, rank should be low. So this is the rank of the correct statement out of k, so rank should be low. And then we break down results for product ads and PSAs, because generally product ads are kind of less creative and less abstract. PSAs are the ones that get really creative, and we also have fewer of those, which is even worse. So if you look at just inputting, say, the image or the slogan, which is a text embedded in the ad, as an input to predict the action reason statement, text is generally a lot more useful alone because it's more directly tied to the message, meaning that the image serves, the image is there to attract your attention, to explain something in the text. It could be to, at the surface, contradict the text, but generally the message is much more clearly encoded in the slogan. which is kind of, we knew this from the start, and so we haven't spent too much time looking at the slogan as input because that's less interesting. But and this is a journal version of a previous method, so we did input the slogan as a with its features. If you look at the action part versus the reason part separately, the action is basically saying go by this, and the reason part is the why, and the why is generally more challenging. So here, this is rank, so lower is better, and for reason, the ranks are worse. If you look at what happens in speech in videos, so these first two results were using images, this last result is doing the same task but on our video ads. So in video ads, there's speech, which you can say is an analog to slogans. But generally, the speech alone is a lot less useful as an input, meaning that the message of the ad is not directly encoded in what people are saying in the ad. And here's a qualitative result where, again, it actually looks very nice, but again, this is the method just needs to select the right statement. So our method is this at the bottom. And VSE on ++ on ads is a standard method trained on our data set where it shows the ad is basically the green regions are regions of importance. What they're kind of hiding is that this person is putting on lipstick, but it's actually a cigarette. And, this ad is meant to look like a beauty ad, but the twist when you kind of, in your perception, when you see that it's a cigarette, not actual lipstick, is intended. And so, but the baseline falls for this. The baseline thinks it is a beauty ad, whereas ours shows a statement that you should stop smoking because it doesn't make you pretty. The reason I got interested in ads is because they rely on common sense, is because they, allude to a lot of human knowledge. So the obvious thing to try next was to look at how we can leverage external knowledge. And here we just mean kind of the classic, old school thing where you look at a knowledge base. And how we can retrieve information from a knowledge base that's a general purpose knowledge base. So it's going to have a lot of irrelevant stuff also. So how you can leverage that to better do the action statement retrieval task. So here we have some of the same stuff from before. So we have visual regions, we have OCR to get slogans, use the slogans to look into a knowledge base. Here the slogan is introducing the Nike Hyperdunk. And so we're going to use all the words in the query to potentially retrieve statements from knowledge base. So the stuff we retrieve is with the blue boxes. So we have Nike, the sportswear company, on the right. We have also Nike, the asteroid, and Nike, the Greek goddess, which are not relevant. And our algorithm has to figure this out. It's not given this information. And what it needs to do here for this specific image is it needs to retrieve a statement like, I should buy Nike sneakers because they will protect my feet. We represent all this information in a graph. But the challenge is that not all of these knowledge nuggets will be relevant. So we need to, learn which pieces of knowledge are relevant. There's also this annoying task that we figured out, which is that the way the task is set up, the method can kind of cheat for cases where there's if there's a lot of images about Nike, it can just learn, and the way the multiple choice task is set up, if there's only a single statement that refers to Nike, obviously the algorithm will just learn to use the word Nike. And so it's not going to reason about the properties of these sneakers that are being portrayed here. It's just going to do the easy thing, which is to match Nike in the desired output to Nike in the slogan. But that's not going to work when it's a less common company or when there's not really an entity to match between input and output. So generally this is, inflates results, but it also doesn't generalize. And so we call this a type of shortcut that the method is using. And it turns out similar shortcuts exist for other data sets, not just ours. So to prevent overfitting to these shortcuts, we basically do something that's, very similar to dropout, but on the token level. So we drop words in the slogan, we drop words in the knowledge base entries, to make training more robust and ultimately improve the performance on the original task. So the way we represent knowledge in a graph, we want to essentially contextualize the meaning of the slogan from external knowledge. So this is the original meaning of the slogan, is this T. K are embeddings for the knowledge nuggets that we retrieve, all of them, including ones that are not relevant, because we don't know what's relevant. And then the alpha terms are learned, and they allow the method to choose which pieces of knowledge to use. The global node is basically our global representation for the image, and we have information coming from V is just visual information proposals. D is slogans, which have previously been contextualized with the external knowledge. And again, the betas allow us to choose what information to use. And then this is trained with our metric learning task, which is to match the image to the human annotated action reason statements. And in terms of masking, in a little bit more detail, we mask our training data to prevent the model from relying too much on word matching or object matching. So 3 strategies we use is to drop words from the slogan, to drop words from the knowledge base query words, the words that we use to query the knowledge base, such as Nike, or to replace entries in DBpedia, which is a knowledge base that we use, with the auto vocabulary token. And I'll start with a qualitative figure first, but basically what this is showing is, so these are 2 ads with the desired action reason statements that we want to retrieve. These 2 show our graphs, where we only show connections over 0.05, meaning only connections that actually matter. So this is the learned graph, and so the edges are these alphas and betas that I mentioned before that allow us to choose which knowledge to use. So this column is kind of the standard way to use knowledge, which is just to treat it as an extra input. On the right is where we use masking to basically make the task harder at training time. And so what we see here, the orange boxes are the boxes. We've changed the color scheme, I guess, but the orange boxes are from the knowledge base. And we actually see a lot more pieces from the knowledge base being used when we do use masking at training time. So now this says nature, rubbish can be recycled, nature cannot. So this is the image that I showed before. And so our method is going to use information about, it's going to look up information about nature and about recycling, and it's going to use that to better understand a slogan here. Whereas the method that doesn't use masking just learns to rely on kind of shallow shortcuts, like matching Nike to Nike or Chanel to whatever Chanel if it's in the statements. And so that is actually, it may work in some cases, but in general, it's not going to be super reliable. So here we have the side task where we evaluate to what extent the method can choose through its alpha and beta weights, can choose the right knowledge statements to use. And our method with masking is, much, much better. A more standard task is, accuracy and retrieval metrics. So this is like prior methods that have used our as data set. The bottom is more of an ablation where we show if V is just visual regions, T is textual regions, K is knowledge nuggets. Basically, if you just add knowledge in the naive way, you don't get almost any boost in performance. So here, these first 2, higher is better. These first 2 blocks, last block, lower is better. But you basically just don't get any benefit from adding external knowledge, which is consistent with what other prior papers have found. So, however, if you do our masking, which is denoted by these 3 masking strategies here, results improve. So now meaning that they improve over both of the previous rows, meaning that now external knowledge actually becomes useful. Thinking of slogans again, just to make explicit what I was saying about the relation between image and text being more abstract, problems that we've looked at before. Some of the same objects are mentioned in both the caption and the image. So essentially you can think of the image and text being redundant in the sense that the same message is transmitted independently across both channels. So you have men in a black shirt, both the black shirt and the man are shown in the images. Here, you're asking who's wearing glasses, and the answer is men, and both the men and the glasses are shown in the image. In ads, it turns out that the two channels are not so much complementary. So they're connected, the image and text are connected in a non-literal way. So this is a super abstract image, and you might say this doesn't even make sense to a human. But basically, the text says they can't afford to wait for evolution, and the ad is about like pollution and the noise pollution in the ocean, and it shows a dolphin that evolved earphones. But the point is, the text says the word evolution, but the image shows a dolphin and earphones, which are obviously not, it's maybe if I just showed you what the slogan and objects were, you can figure out what's the connection, but I think that's unlikely. So it's actually a very, very indirect connection. But it still makes sense because these image and text still showed up together, so that they do have some connection. It's just a different type of connection. So in this paper, we tried to understand what kind of images and text are co-occurring in parallel, meaning that they actually say the same thing. So here you have a bottle of clean water, and the text says purified drinking water. But there's also image and text that did co-occur in the sense that this is a slogan and image from the same ad, but they're actually non-parallel. And 3 ways of being non-parallel that we came up with from our data set were that starting with this, maybe one can be ambiguous. So if you see a Coke or a Pepsi bottle squished between a sandwich, this doesn't necessarily make sense. If you read the slogan, which says a bite's not right without it, then that becomes a little bit more clear. So one modality can be ambiguous, one modality can just purely be decorative, and usually this is the image. Or even more interesting but more challenging, the image and text could actually appear to be opposite to create some sort of deeper meaning, which I want to get into because it's just ad designers being super creative. We also try to look at what kind of relations between symbolic and more literal, more objective concepts we can find through this metric learning that we did, because we did project both essentially object words and more abstract words from our action reason statements into the same space, and we looked at just neighborhoods in this space. So we found that if you have the symbol or concept of comfort, which you might find in our reason statements, like you should buy this because you'll be comfortable or whatever, that in terms of its neighbors in this learned space where we project a whole bunch of stuff into the same space, its neighbors there are going to be things like this, are going to be objects like pillow, bed, blanket, couch, and rug. Makes sense. If you want to demonstrate being cool, these are the objects that you would use, basically. If you want, and then you have 2 objects that both derive from tomato, but one of them actually correlates with the concept delicious, and the other one correlates with the concept healthy, in the sense that these are neighbors in the joint space that we learn. And we also discover some associations between image regions and text. So we got these associations again in our cross-modal space just from the action reason retrieval task. We didn't have any annotation for Oreos or for ketchup or Pepsi or lipstick. It's just that these were mentioned in the action reason statement, along with a whole bunch of other words, right? So for very concrete concepts like Oreos and ketchup, we can actually localize them. So these green things are boxes that most correspond to this concept. So we actually were able to localize them without, trying to, and without having any supervision for Oreos or for ketchup. So that inspired the following approach, which now has nothing to do with ads and goes back to something a lot more mainstream, like object detection. So we have this paper where we try to learn object detection models from a weak supervision in the form of captions. So whether captions are weak supervision or not is a little bit maybe controversial. Our point here is that people generally provide text when they upload photos, and this text is going to be in the form of a caption. It's going to have a lot of words that are not really the object that is in the images. Here we actually use captions that are crowdsourced, that are written to be clean descriptions of images. But what I'm interested in right now is how we can extend this to even more naturally occurring and noisy captions. So the point here is to, obviously work in using image level supervision to do the localization task exists. We're trying to make this a little bit Here, the supervision is even more weak in the sense that it's not object labels, it's captions, which may or may not mention all the objects and may also mention things that are not objects that we should ignore. So we want to go from captions to having localization at test time. The way we do this is a little bit not quite satisfactory to me, which is that we do actually use a small amount of supervision, but it's very small. And there's ways to do it without supervision. And it turns out the supervision, even though we have it on just a single data set, generalizes to others. But point is, we do just learn, a text-only classifier that, given a caption, produces the labels for this caption. And we can do this. We do get these object-level labels from an image data set, but in theory, it doesn't have to come from an image data set. There doesn't have to be a connection to an actual image sample. So the challenge here, is that, again, the caption is not going to mention everything that's relevant. So if you have this image, so it says person in tie, for example, and a bunch of other persons in a bottle, the captions are not going to mention all these objects. You have people watch a man delivering a lecture, wearing a suit, so on and so forth. The word tie is never mentioned. And there's a few other people that have looked at this task before, but haven't actually proposed how to use this for object detection. So our point is here, the object tie cannot be extracted through lexical matching because it just doesn't appear anywhere in these captions, but a human can kind of figure out if there's a person delivering a lecture at a conference, maybe they're probably going to wear a tie. So we can learn to map from captions to labels efficiently. This figure shows basically different ways of doing that, where this text classifier is kind of the unappealing approach that I mentioned. You could just use, some sort of word embedding similarity or a word embeddings learned for this, for your data set, or you could do exact match, meaning if the caption mentions tie, you assume tie is a label for this image. You could also rely on a handcrafted, like synonym dictionary, essentially, because if it says man and the label is person, you still want to say, yeah, that man and person are the same thing. This figure basically shows that it doesn't matter if we use 100% of the data that we have for this text classifier or just 5%. Basically, recall doesn't much change in terms of the labels that we can retrieve. So this figure here was evaluated in terms of, do we get the right pseudo labels at the image level? This is actually, actual detection performance with these pseudo labels that we get. The top part here, these two use ground truth labels at the image level, and so these are going to be upper bounds here. And this is on the VOC 2007 test set. So we have a model that uses COCO image level labels and VOC image level labels. And we're trying to match this with our noisy strategy. We're trying to match this ground truth, the GT label COCO. The second block of results are different ways to map a caption to a label. And the text classifier we use is the best one. It actually comes fairly close in terms of overall precision here. So we have 46.3 and 43.1. They're actually pretty close. Other ways of obtaining these pseudo labels are inferior, but not that much inferior. So ours is 43.1. The next best thing is 42.5, but it relies on a handcrafted dictionary. The next best thing is 41.7. But the boost of this text classifier over other ways of generating the pseudo labels actually transfers to other data sets which have different data than the data that we use to train our text classifier, which we're encouraged by. And so that was basically going from ads to ads have these essentially caption-like pieces of information, and so whatever we discovered in the ad space, we try to apply in this more mainstream space of object detection. And this is something that I'm interested in, kind of how to learn detection models from noisy language supervision. And related to that, we started looking at now back to the slightly more niche stuff, which is we started looking at political articles, and kind of how they construct narrative. So this is very similar to the motivations of our ads work, but now looking at political articles where you're going to have a lot more text. These are not going to be as creative because these are going to be naturally appearing images for the most part, but they are going to have some sort of bias. And the first thing we did is try to infer political bias here, based on just from the images alone, based on the intuition that, and, there's research showing that there's, left-leaning values or values associated with the left and values associated with the right. So here we have this very silly figure that tries to kind of show this intuition, but is obviously, this is things are more complex than that. So we want to study political leaning of an image just from the image itself at test time at least, and basically predict whether an image appeared in a left-leaning or a right-leaning source. This is going to be our noisy supervision that we use at training time. Which is to inherit the label of the source and apply it to all the images that appeared in this news source. And then at test time, we're going to have some supervision because we don't want to be trying to classify the political bias of a cat image, because there's also going to be a lot of images that are not going to have any sort of bias. So we have a multimodal setting where we have images with paired lengthy articles. For training, and this is basically, I said this already, for training we have weak labels, so the bias of a media source, and we're going to get the bias of a media source, which is much easier to get because it's just, the whole media source is just one label. And we get this one label from a website called Media Fact Bias Check. There's other websites like that. We spider these media to find articles about controversial topics, whatever was controversial at the time that we did the work, and we get about 1 million images unique images total after you do deduplication, as well as their associated text. And for testing, we have about 1,000 images that were clearly labeled left or right, in other words, having a bias by a majority of annotators, as opposed to having an unclear bias. The way our method works is we actually have 2 stages. And I said that we don't want to use the text at test time, but we do use the text as an auxiliary modality at training time. And the reason for that is that the task is actually much easier, maybe not much easier, but easier from text than from images alone, in the sense that bias is more obvious in text. So at first, we're going to learn a document embedding from the article. So this is just a way to represent a text. And we train this document embedding, so it's actually just a doc2vec on our data set. And you can think of this obviously as an unsupervised task. Then we fuse the image features from a ResNet and the doc2vec features from the text and train a classifier. Then this is really just a way to learn image features that are going to be more relevant, this bias prediction task. In stage 2, we get rid of, we keep the features of this ResNet, which are now appropriate for the task, frozen. We get rid of the text input and we train just the last layer, which is like a classifier, to now use the features that are appropriate for bias classification to actually properly classify left and right from just the image. The quantitative results are not so interesting. Something I think is interesting is a way to actually, more tangibly demonstrate bias for something that's fairly fixed, where visual variability is going to be controlled, which is faces of well-known politicians and how they appear in left and right-leaning media. So we have faces, we have pictures of Trump. At the time, it was what was, I guess, more relevant was Clinton and Obama. And so for these pictures, we have a lot of data for Trump in left-leaning sources, Trump in right-leaning sources, and we want to see how these are actually different. And to do that, we used a generative model that we developed in a prior work, which basically models left and right using distributions over attributes that are predicted from a separate data set, so we don't require any extra annotations. And this is what we get. So the method we use in this prior paper is, gives us blurry results, which is fine. The point is to see, how these blurry results are going to be modified. So these are the original images. These are reconstructions, which again are blurry, but that's not what we focus on. So now we want to modify all of these images to appear we're going to want to push them very far to the left and very far to the right. And I say very because we, exaggerate kind of the shift just by, applying a scalar to make the pattern more obvious. So if you show, the same pose of Trump on the left, even when he was smiling, he actually starts being angry, whereas Clinton and Obama are going to become happier generally. And so Obama, interestingly, here is looking down. So on the left, which is going to be supportive of him, he's going to start looking up. And this is something that our model automatically learned, that looking up tends to be a more favorable portrayal. And now if you do the reverse, if you want to show Obama or Trump on the right, he starts looking like this, which is, I think, very, very unrealistic, but probably this is what Trump would look like as a more positive portrayal, as a very, very positive portrayal on the far right here. Clinton, when she's smiling, starts being very angry. Obama, similarly, when he was actually looking up, now starts looking down. But unlike Trump and Clinton on the kind of the opposite end of the spectrum, Obama doesn't look angry in any of these photographs, which is interesting. Quantitatively, back to the bias prediction task, we break up our results a little bit by category, and we compare it to a bunch of baselines, but this is not all that interesting. So I'll move on to this next task, which was to try to retrieve. So now we're going to look at the text a little bit more explicitly, the text that we have in these political articles, and politics is basically our data set, and to try to do something that in principle is more classic, which is cross-modal retrieval, but in this much more challenging domain. So one thing that you might do retrieval on is COCO, where again, images and text are going to be essentially redundant. Not that it's not a difficult task, but it's just a different type of task. And here we have something where you have an image of a protest. The text actually, you can probably as a human match this text to the image, but it's a more indirect relationship. So it says, immigrants say President Donald Trump's administration has become almost everything they feared, and so on and so forth. This is something about guns. This is, something about LGBT rights. We want to be able to do cross-modal retrieval in this space. So most prior work assumes that images and text are highly aligned, but text in real-world media is not so well aligned, and the image might just visualize different aspects of the text or vice versa. Our data set, our politics data set is much more visually diverse and much noisier too, because we harvested it from the web. And also something that we don't quite leverage here, but the paratext is often much longer than caption, which poses another challenge. What we're really interested in is how the two modalities are complementary. So this is again a slightly exaggerated complex example, but you have this image here, and the authors of the article that chose this photo are using it as a form of visual rhetoric, and the modalities are complementary, meaning that this image of the Greek goddess of justice Themis can be paired with any of these texts. So it can be about Supreme Court on Friday ruled that same-sex couples can marry. It can be about the future of abortion, could be at stake. The grand jury's decision not to indict the officer illustrates both the power and the limits of the Black Lives Matter movement. The Supreme Court gave Trump the go-ahead on the border wall using military funds. So all of these can actually appear with this kind of image. On the other hand, this particular text can be illustrated with very visually varied images. So these are all about border wall, but it's literally the border wall, an IC officer, an immigrant child, or a protest. All of these can appear with this text, but they're very visually diverse. So what we propose here is to essentially make the visual representations more aware of semantics beyond just what a triplet loss can give you. So in these illustrations, we have text being denoted by circles, images being denoted by squares, and the basically xi and yi are an image and text that appear in the same article, and same for the green things. So the color denotes which article something appeared in. Green and blue images may actually even though they appear, xi appears with yi and xj appears with yj, these two images are not necessarily going to be visual neighbors. And here we're trying to say that iy and ij are actually semantically in the original doc2vec space are going to semantically be related. In the new cross-modal space that we learned, they don't have to be neighbors, but they are originally semantic neighbors, and we want to preserve that. Existing methods like a triplet loss, or actually other losses too, stronger metric learning losses that we tried, don't necessarily preserve semantic similarity. So, they are going to put the x's and y's closer, but they might do that by pulling the y's that were semantically close apart. And so what we do is that so these two texts that are semantically similar may actually be stretched apart, and the images may undesirably, remain far. So what we do is we still use triplet loss, but the way we apply it is to bring is within the two modalities, within the text modality and within the image modality. So essentially you have this kind of quadruplet of things that we bring together. In a little bit more detail, these are 4 pieces of text denoted by these triangles here, 4 images that should be brought closer by triplet loss because they actually co-occurred. Our point, however, is we want to first learn a model of text semantics with doc2vec and to keep things that are semantic neighbors close in the new space, which applies to both the text and the images. So texts that were originally close, we're going to enforce that they be close in the cross-modal space, as well as the images that appeared with them. So now all these images, even though they're visually distant, will be enforced to be close because their paired texts were close. So with this, we compare to kind of as strong of a combination of existing metric learning losses that we could come up with, including a kind of a more vision language method, this PVSC. We evaluate on 4 datasets. 2 are generally aligned and 2 are generally not aligned. So politics and good news are both different datasets with articles. Conceptual captions is less well aligned than COCO, but it's still slightly more literal. We have this K-way retrieval task. Rather than evaluating rank, we retrieve whether we got the right, it's again a multiple choice task, and we outperform most of these prior methods. But more importantly, if you look at the kind of images that were not neighbors but are brought closer, these are actually the two pairs of images that where our method had the most impact, in the sense that we're showing the smallest ratio of the distance between these two images in our space versus a space that they get assigned, versus the baseline triplet loss space. So these are obviously very different, but they're related because they're both like about the EU and about justice. And something that we did a little bit more recently is to come up with ways to weight samples in terms of essentially how abstract they are. So how much they should be prioritized in the overall, triplet learning loss. And our point is things where they're neighbors, where we do what we did in the previous part, which is that we look at textual neighbors, we look at the corresponding images for these textual neighbors, and we measure how visually diverse the neighbors are. So so you have this image where you have these children with the Israeli flag, and a former Netanyahu aide is the key figure behind an unprecedented government decision to allow so on and so forth. This is a case where it's much more literal. So you have a laptop and you have a description of the laptop. So the corresponding visual neighbors are going to be the corresponding images for textual neighbors are going to be these in the bottom and these at the top. So obviously these are much more visually diverse. And so we say this is a more abstract case and we're going to prioritize it in our loss. I'm going to skip this. These are basically types of image text pairs that are weighed highly by our method through different metrics. We outperform lots of other ways to weight samples on most of the data sets except for COCO, which we're not really aiming for in the sense that it's more literal. In terms of cross-modal retrieval, given the word justice or patriotism, this is what our method retrieves, which we think is much more relevant, and this is what the baseline retrieves. And so with that, I'd like to thank my funding sources and my students. Happy to take questions.
Thanks, Adriana. So if anybody has questions, feel free to post it in the Q&A section of the interface or on the chat. We'll keep an eye out on both. There is one question so far, and I guess you can see it now, but
Yes.
a question on how you got all the ad data.
Sure. How did you manage to get the ad pictures? So we just crawled them. Yeah, we generated a giant list of topics for what ads might, for different ad topics, and this is in a supplementary file. It's a giant list that my students came up with, and then for each of these keywords, we basically, scraped Google Images to get images. We then had a process to not everything we scraped was actually ads images, so we didn't want to actually run every image through human verification. So we did human verification on a subset of images, and we learned a basically ad versus not ad classifier, which worked really, really well, which was kind of surprising. And then we applied this classifier to clean up the data. And then we had a secondary process where if something went through further annotation wasn't actually an ad, the annotator could say it's not an ad. But that happened for very few ads. So we had a combination of like human verification and actually learning what's an ad. Thanks for the question.
While we wait for any other questions, I was curious about one piece where you were talking about collecting annotations for the signifiers and the signified, like for the symbolism, ground truth. I was curious if you experimented with trying to just sort of learn this from external knowledge or just sort of mine it in some way, and if that failed and you went down this route, or was this the first thing you thought of doing? Or
yeah, so I think I think we did try something like that. So the basic thing we have is just a straight up standardly trained classifier. I think we did play a little bit with using external knowledge for the symbols, but as part of a separate task. And actually, the symbols, just as I was talking to someone this morning, I kind of got re-excited about that idea, because there is I think when we did this, there wasn't as much interest in common sense, but now there is, and so I think there are ways we can try to use either like more transformer like pre-training as a form of external knowledge or external knowledge bases. So we'll probably revisit that and see what we can get. Maybe we can treat whatever we have annotated as a just a test set and see what we can get from existing resources.
Yeah, and I wonder if like similes or cliches are like particularly good sources of identifying what kinds of objects people use to indicate what kinds of values. Like I don't know if as a bullet is just a thing, or I'm not a native speaker, but like things of that sort.
Right.
Yeah.
So I did. I am working with someone who had earlier looked at like metaphors in language, and I guess whatever is a metaphor in language could be a good, good candidate for being a symbol.
Yeah. Harsh has a question. A recent trend in language or vision in language is to pre-train on a large corpora of data like conceptual captions, wiki. Do you think there is any hope of using that data to leverage the context that may be present?
Yeah, I'm sure it's definitely going to help. We haven't much played with that in this setting. We have the standard forms of pre-training, like initialize embeddings to something sensible. But for anything cross-modal, we haven't. Some of the embeddings we use are like cross-modally pre-trained, but not the kind of like actually modern stuff that you're talking about. So we haven't experimented with that too much. On the ads data set.
Oh, there were actually other questions that I missed. Can you explain how the DBpedia gathered knowledge?
Right. So we just want to get a little bit of context, like what is Nike or what is nature or what is recycling. So we just get whatever comment exists in Wikipedia about this concept. And we try to, fuse this with other features in our model. But there's other knowledge bases we can use that are a little bit more structured, not a whole comment. Maybe we can get something that's more of a graph. This is just what we play with at the time. I do see the other questions. Let me see. Parallel and non-parallel relationship between image and text. Did you manually label these? How did the algorithm manage to learn parallel versus non-parallel. So thanks for the question. So we did label, actually a very small set. We did label about 1,000 images with parallel and non-parallel. We had a lot of trouble, even though what we were going for was clear to us. It was really hard to convey this to annotators. So we thought maybe next time we'll hire, English majors or something, undergrads that would understand this a little bit better. It's really not their fault. It's kind of our fault for failing to explain the task, even though we tried. But we do have some annotations, and for some of them there is reasonable human agreement. And in the algorithm, we actually tried a lot of different algorithms to predict parallel or not parallel. Some of them work better than others. So we actually used this was done a while back, so I don't fully remember, but we looked at, for example, if you extract the top objects in the images and you extract the top words some number of words from the slogans, how much overlap is there? And if there's a lot of overlap, that's parallel. We also looked at things like memorability on the vision end as a proxy for maybe not being parallel. We looked at measures of concreteness just on the language space as a measure of non-parallel too. But nothing worked really great. The things that we thought would work well didn't work too well, probably because we don't have that much data. Do you think voice recognition can be used? Yeah, so we did use voice recognition. I didn't say this. When I talked about speech, we did actually run voice recognition on that speech to get representations of what's being talked about in the videos. But we can probably do better than what we've actually done so far. Far left and far right. Could this be applied to somewhere in between? How many pictures do you need for an accurate model? It can probably be used for things in between. I mean, our model actually, you can tell it how much to exaggerate, so you can tell it to not exaggerate. It's just we wanted to really show how much of a difference there really is just in the data set itself. And how many images do we need for an accurate model is not something that I remember. We originally, for the generation model, we trained it on our ads data set, which no matter how we split the data is capped at 60,000 images, but in terms of faces is even less. So it's something on the order of tens of thousands, maybe 20, 30,000, which is why it's, we had to use something that gives us blurry results.
I have one more question. This is Harsh. So you had mentioned how, you mentioned using captions to for an object detector, and you had mentioned that in those cases it's possible that even for objects that are not mentioned in the caption, you can detect those too. And I was wondering whether you observed this behavior in your evaluation, where for an image or for basically a data set of images, you had some clue that there is an object present which was not mentioned in the training captions data set.
Yeah, we didn't. I think we don't have any results doing, measuring that separately. But that is something that I'm interested in, and something you will probably pursue further. But I don't think we had a breakdown. Probably, if you look at the accuracy for different object categories, probably there's some that are less likely to be mentioned. So I can probably look at that and try to come up with, a pattern. But it's not something where I have a conclusion ready for you, which is, it's actually a really good question. So, maybe I'll have an answer next time someone asks something like that.
Cool, thanks.
Thanks for the question. I don't know if we're out of time. I guess there's one more question I can answer. Could you briefly mention what is being considered as a weak supervision in one of the projects? Yeah, so I didn't properly define weak supervision. I just mean that I don't want to have annotation for everything that I do. I don't want to have labels for left or right labels for all the images. I don't want to have object labels at the box level. So that's kind of, it's easier to define weak supervision in that setting. I don't want to annotate so there's some VQA data sets that where there's kind of a knowledge base that's a little bit more relevant to the questions. Here we want to work with a general purpose knowledge base where there's going to be a lot of noise in what ends up being retrieved that's not useful for our task. But yeah, it's not a very clean definition of weak supervision.
All right, I think we're out of time. Thank you, Adriana, for giving us this very interesting talk. Thanks, everyone, for asking your questions and engaging. And
Thank
have
you
a
very
good rest of the week.